We want to return to some concentration units talking about mole fraction, which is going to be useful to calculate some of those colligative properties. So mole fraction, the symbol for mole fraction is a capital X. It is the fraction of moles of one substance to all moles in the solution. So the equation, the mole fraction of A, so this capital A here is just stand-in for basically chemical formula, whatever the chemical formula is of your substance. So the mole fraction of A, so you'll notice it's X, the A is now a subscript, and it is moles of A to total moles. So how many moles of A do you have to total moles? So this is very similar to the percent concentration. You'll note that that was mass of solute to mass of solution. This is moles of one of your components to total moles. Same idea where total moles is just you add up all of the moles that are in there. Mole fraction is mostly used where the solvent and solute have the same phase. So for example, dissolving alcohol in water, because it can be hard to distinguish what exactly is the solvent. Do you have more alcohol or more water? How does that? There's kind of a variable scale. You can either can be the solvent or the solute. So you want to talk about all of those mixtures with the same language. So that's where mole fraction really comes up. Any fraction, you also note on the bottom it just says total moles. It doesn't have to, or it's in the top it's just moles of A. You can define the mole fraction of the solvent or the solute really easily. All substances can have a mole fraction. The other advantage is that mole fractions are readily calculatable for mixtures with more than two components. So when you have, say, methanol and ethanol and water, what's the solute? What's the solvent? You know, when you have multiple things, how do they kind of all mix together? And so you can just kind of define the mole fraction for whatever you want. How many of the relative things do you have? Let's look at an application of calculating a mole fraction. What is the mole fraction of methanol, CH3OH, in a mixture of 50 grams of water and 50 grams of methanol? So just like we've done previously with the other concentration units, we always want to start by being able to calculate this concentration unit as a way to characterize a mixture. You have 50 grams of water and 50 grams of ethanol. What's the mole fraction of methanol? All right, if we take our kind of unbiased approach, we can always start by reading a problem to ask, what do we want? In this case, it's mole fraction. So mole fraction, again, concentration unit has an equation. The mole fraction of A is going to be moles of A divided by total moles. We want methanol, so we can replace those things. It's not just going to be A. We know it's methanol, so I want moles of methanol divided by total moles. Do we have those variables? Do I have moles of ethanol? Do I have total moles? I don't have moles of methanol, but I do have it in grams. So this is common. You know, you made your mixture by mixing together. You measured out masses. You need to turn them into moles. We've seen that previously. For total moles, that would be adding together the moles of water and methanol. So we already needed to calculate the moles of methanol previously, so we're going to do that again. But we're also we're going to need to convert water into moles. So one of the kind of rubs, if you're calculating mole fraction and you have a bunch of masses, you just turn all of them into moles. So it's just a good exercise. It's like you're back in Gen Chem 1, turning masses into moles.
All right, I want the mole fraction of methanol. We want to recognize our concentration units. Mole fraction is capital X, CH3OH. You put that little subscript for whatever you're describing, and we know that that's going to be equal to my moles of CH3OH divided by total moles. And that total moles we can expand out more because we know that's just going to be the moles of everything added together. Just like mass is additive, so are moles. So moles of CH3OH plus moles of water. Oh, whoops. So if I want to figure out the mole fraction of CH3OH, or conversely any component in the solution, I need to know the moles of basically everything that's in there. That is not given to me. Just like we saw previously with molarity, the amounts of the different components are written in mass. They're always going to be given in mass, which is, the useful and kind of common representation. We need to convert those into moles. So we can do that for each component, convert to moles, grams to moles. So we're going to use the molar mass. I have 50 grams of water. I can use the molar mass of water, 18.02 grams of water per 1 mole of water. That is equal to 2.8 moles of water. And if I have 50 grams of my methanol, CH3OH, by that, the molar mass of methanol is 32.05 grams. And that gives me 1.6 moles of CH3OH. So what I've done is I've gone from the mass representation to this molar representation, where now that is reflecting the number of molecules of each. I started with 50 grams of each, so the same mass, but each methanol molecule is larger, reflected in the fact that it has a larger molar mass, meaning I have fewer total molecules of methanol than of water. Or conversely, you need more molecules of water to get to the same mass of methanol. We can plug that stuff in now. We can get that the mole fraction of methanol is going to be equal to 1.6 moles divided by 1.6 moles plus 2.8 mole, which is equal to 1.6 moles divided by 4.4 moles. Those moles are going to cancel out. And I get the mole fraction of CH3OH is equal to 0.36. So overall, we can see that the mole fraction is very similar to a percent concentration, but we don't multiply by 100. So we leave it as a fraction, even though it's a decimal, but we could convert that to a fraction. So a couple of things about mole fraction. Because it's moles of one thing out of total moles, this value always has to be between 0 and 1. And how we can interpret this 0.36 is that 36% of the molecules are methanol, or 0.36 of the moles. But this description is by molecule. And so we can see that mass-wise, this mixture was 50-50. It's 50% methanol, 50% water. One of the things as a result of that is you using a pure mass description, you can't call one of these things the solvent and one the solute, which is fine because mole fraction doesn't care. Mole fraction does not care what the solvent and what the solute is. It's just telling you what percentage of the molecules or what fraction of the molecules are that thing. So the mole fraction of methanol is 0.36, so 36% of the molecules are water. Not equal by mass, or they're equal by mass, but not by molecule. The other thing is that the mole fraction of the methanol plus the mole fraction of water has to be equal to 1, because this is a mixture of these two things. If you add up all the mole fractions, they have to equal out to 1. So if we know the mole fraction of this is 0.36, that means we can figure out that the mole fraction of water is equal to 0.64, because 0.36 plus 0.64 is equal to 1. So again, mole fraction doesn't care. We would, now that we know there are more molecules of water, we'd probably call that the solvent if we really needed to, but in this case, we don't need to, and mole fraction does not care. It is able to tell you that 0.36 out of 1 molecules are methanol, 0.64 are water. So that is the relative ratio or relative fraction of each of them. 36% of the molecules are methanol, 64% of the molecules are water. Mole fraction is not represented as a percentage, but we can interpret them in that way. And so this is really, mole fraction is useful in cases where you want to describe everything. You know, you don't really, either you don't care if you have a solvent and solute, or you want to describe the solvent. This is the only way that you can describe the solvent. Molarity and percent concentration are all just based around solute. And if you also just kind of want to describe all of it. The other thing that can happen is you can have more than 2 things. If, say, you dissolve in water, you put methanol and ethanol and propanol, right? You got all sorts of things mixing together. You can have more than 2 mole fractions. So mole fraction in a lot of ways is our most variable concentration unit because it doesn't depend on what the solute and what the solvent is. You can describe any component of any mixture. So this is really common when you're mixing liquids inside of liquids or solids inside of solids, gases inside of gases. Whenever you're kind of maintaining the phase and you're mixing a lot of things together, that's where mole fraction really, really is useful.
So mole fraction is really useful. It gives you a really chemical perspective. It's like a chemical version of percent composition, which is really nice and has a lot of applicability. It is definitely something that will come up again and again. But really one of the places where we really have to kind of use mole fraction is when we have more than 2 substances in a mixture. It's not like you have a solvent and a solute, but maybe you have a lot of stuff that's all mixed together and you want to kind of describe them all equally. So for example, air. Dry air is mostly, it's mostly made up of nitrogen, oxygen, and argon. That's over 99% of air. So rounding to 2 digits after the decimal, that adds up to 100%. And so, you know, you can kind of think about, well, what does that mean? You know, really, you can talk about nitrogen as the solvent because it's 78% of molecules. You know, there's a lot of them out here in this drawing. There's a lot of nitrogen here. So sometimes you can describe nitrogen as the solvent. But one of the things we want to think about is we always think about the solvent. One of that kind of implies that the solute is functionally different, right? Like when salt dissolves in water, it's very different than solid salt. But when oxygen dissolves in the nitrogen of air, it still looks a lot like oxygen. It still behaves in the same way. It's not so cleanly entirely dissolved in nitrogen. And so that's one of the reasons why we would say we kind of use mole fraction instead to say, well, the oxygen's 21%, 0.21 mole fraction of the molecules are oxygen. We especially do use mole fraction in the case of gases because we know from the ideal gas law that really like pressure and volume, all that really matters is the number of gas molecules. So that's why we prefer mole descriptions as opposed to percent composition that's based around mass. And then there is kind of flexibility. Water can come in if it's, say you live on the upper Texas coast and the humidity is a little high. But even the most humid air, that's say tropical regions, you're still only up the mole fraction of water is 0.05. It doesn't get very high. It doesn't relative to say the mole fraction isn't that high, but 5% of water molecules is very uncomfortably humid, and so but that is what it gets up to. You're not up in actual real water. All right. No participation questions in that video. We got one more video. See if we can find one more question for participation 127. I'll see you there.